Ever wonder how engineers make sure a swarm of drones flies in perfect sync without crashing? Or how self-driving cars navigate busy streets without a central command? It's all about distributed control systems, complex networks where each part must work together but with limited communication. Today, we're diving into a breakthrough that's making these systems smarter, safer, and more efficient. Let's start with a simple analogy. Imagine coaching a soccer team. You want players to pass the ball strategically, but they can only communicate with a few teammates. How do you design the rules so the team wins? That's the core challenge of distributed control, balancing coordination with constraints. In control theory, the linear quadratic LQ problem is a classic recipe for optimal performance. It defines goals like keeping drones in formation and adjusts inputs, motor speeds to hit them. But here's the catch. When scaling to thousands of drones or a power grid, traditional methods hit a wall. They either oversimplify the system or become computationally impossible to solve. Enter group-sparse feedback control, a smarter way to design these systems. Instead of every drone talking to every other, we restrict connections, like a soccer team where players only pass to specific teammates. This reduces chaos but introduces a new puzzle. How do you design controllers that work with these restrictions, not against them? The research tackles two key problems. 1. DFT-LQ, distributed LQ with fixed topology, a per-written playbook where each player knows exactly who to pass to. 2. SF-LQ, sparse feedback LQ, a system that discovers the best connections during design, like a team adapting mid-game. But here's the twist. Existing solutions rely on convex relaxations, math shortcuts that simplify problems but often miss the mark. The authors took a bold approach, a nonconvex optimization framework that directly addresses these challenges. What's nonconvex optimization? Imagine navigating a landscape with hills, valleys, and unexpected twists. Unlike convex problems, which have one clear peak, nonconvex ones have multiple local maxima. But this complexity lets them model real-world systems more accurately. The team used group L0 norm regularization to enforce sparsity, essentially telling the system, only activate the connections that matter. Their secret weapon? A new algorithm called PALM, Proximal alternating linearized minimization. It tackles these tricky problems step by step, avoiding the pitfalls of older methods. Unlike previous approaches, PALM doesn't get stuck in endless loops or fail to converge. The researchers even proved it works under mild conditions, ensuring it finds meaningful solutions even in complex scenarios. But here's the kicker, PALM isn't just about control systems. It's a game changer for any field dealing with optimization. Think of it as a supercharged GPS for complex puzzles. Imagine a drone navigating a storm or a power grid, adapting to sudden outages. PALM's flexibility means it could handle these real-world chaos scenarios, where old methods would fail. So how does PALM work? It combines two powerful ideas: gradient analysis, like checking the slope of a mountain to find the peak, and regularized augmented Lagrangian, a fancy math tool that balances different parts of the problem, like a recipe with just the right ingredients. The real magic. A convergence proof that works even when traditional methods fail. Here's what makes it robust. 1. Sufficient decrease. Every step gets you closer to the solution, like taking a guaranteed step forward in a maze. 2. Boundedness. The solution doesn't go off the rails, even if the puzzle's rules are weird. 3. KL property. A mathematical rule that ensures you don't get stuck in a flat, unchanging area. This isn't just theory, it's a revolution. The same math could transform fields from AI to robotics. And the best part? The research doesn't stop here. They're already exploring how fast these solutions converge, and how to tweak them for even more efficiency. In short, this work is like giving engineers a more precise tool to build the future of connected, intelligent systems, where every connection is intentional and every decision is optimized. Next time you see a drone swarm or a smart grid in action, remember, behind the scenes, math is making it all work. Stay curious, and let's keep exploring the intersection of theory and innovation.